exam. If you have questions about any of it, bring it to my attention, and I'll try to answer any questions you might have about the questions that are not answered in the solutions manual, because the solutions manual has all the answers as well. So the answers have been duplicated in a sense. You have my answers, you have the solution manual answers, and between the two you are able to make a decision. Okay, so last time we talked about IR spectroscopy. Let's just go over this briefly. And we said that IR is the method of choice for figuring out what kind of functional group you have. And so the nice thing about IR is that it will actually distinguish between the various types of carbonyl groups that you have in a molecule. So esters come at a higher frequency, not as high as acid chlorides, amides at a much lower frequency, and so on. You don't need to memorize this. I'm going to give you a little bit of information that tells you how to make sense of this. And of course, it's going to have something to do with how important this kind of resonance structure is for the particular carbonyl compound. And so for nitriles, of course, are a special category because they have triple bonds. These come at a completely different stretching frequency. I mentioned that we will be talking about nitriles in the same chapter. However, they are different. But yeah, I think you'll see why we do that. Okay, so let's get back to this IR business. So this is fairly easy to see, the correlation between what you have attached to the carbonyl carbon atom and what stretching frequency you have. It's fairly easy to see for an acid chloride. Acid chlorides come what, around 1800, right? So that's pretty far away from where a ketone comes. Ketone around 1700. This is all 100 reciprocal centimeters away from that. Now, remember that chlorine is electron withdrawing compared to carbon. And so this resonance structure, which would be perfectly okay if you had something other than an strong electron withdrawing group, this resonance structure is not particularly important. It's not particularly important because why? Well, because that chlorine is sucking electron density out of a carbon atom that's already positively charged, which means that this is the major resonance contributor in the case of an acid chloride. And so you have the full double bond character. This doesn't contribute. And that's why the pi bond is short and strong. Okay? And so this pi bond is harder to stretch, and that's why the stretching frequency is so high. Okay, we'll come back to some of this in a bit. For NMR, proton NMR, this turns out to be an important correlation. That is, if you have a CH2 that's next to an oxygen, already you know that CH2 group is going to be de-shielded. It's going to be de-shielded because oxygen is electron withdrawing compared to carbon. But it is more de-shielded when you have an ester and less de-shielded when you have an ether. And the difference here is about 0.5 ppm. So if you have an oxygen in the molecule and the CH2 is around 4, that's a dead giveaway for an ester. Okay? And if it's at 3.4 or 3.5, whatever, then that's pretty much an ether. And so that 0.5 ppm difference is the electron withdrawing effect of that carbon atom, that one right there, that has a partial positive charge in one of the resonance structures. Okay, so just remember that. Now the alpha protons here around 2 ppm, that's not diagnostic. So whether it's a ketone or it's an aldehyde or an ester or whatever, they're always around 2. So that's not going to help. So even an amide is around 2. So now if I look at this is proton NMR again, the NH, well, anything that's NH, OH, SH, whatever, can be hydrogen bonded. Those things will wash out. So in other words, if I have a peak that I suspect is an OH or an NH, I just take my NMR sample, I add a little bit of D2O, shake it up, and then that peak should disappear because of the exchange. Okay, so this would be the NH. Now, sometimes these are, depending on the concentration, how much water there's in your sample and so on, These peaks can be really broad to the point where you may not even see them because they blend into the baseline. But in any case, they are usually pretty far downfield and they wash out. The alpha protons, again, nothing really to say about that. N8 or N-methyls around where you expect. This is what I said last time, that when you have two methyl groups, they're diastereotopic. They're actually distinguishable. And you know, NMR is just a really neat tool. You know, you just can't imagine this until you think, well, gee, you know, yeah, we have that resonance structure that places a double bond here. And so that resonance structure is important enough that those two methyl groups are actually, on the NMR timescale, in different environments, and they show up as separated peaks, and separated by quite a lot, actually. And so they're chemically non-equivalent. The first time you see this, you know, you almost can't believe it. You think, gee, is that really possible? But it is, you know, and so it's a way to tell that you have an emit. So even though the exchange rate is fast, about 10 times a second at room temperature, of course, when you heat it up faster, slow enough for the NMR so that they appear frozen in space. C13, not a lot to say. As you would expect, as the resonance structure that has a double bond here becomes more important, the chemical shift of the carbonyl carbon becomes less and it gets shielded. And so, but the correlation is not perfect. As you can see here with the chloride, it's 169. With an ester, it's 170. And that presumably is because the lone pairs on the chlorine shielding the carbonyl. The alpha carbon is, you know, it's always around 20 somewhere. Again, not particularly helpful. For nitriles, this is proton, that's why it's red. Proton about 1.3. Carbon, quite different from a carbonyl, right? This is around 117. Also different from a carbon-carbon triple bond, because this now is electron withdrawing compared to carbon, so he shields it. So these are on 70-something. This is all the way up past 100. So you don't have to remember these numbers. You know, if you need numbers like that, you look them up. But so in the problems that you have where you have spectroscopy, don't rely on memory for chemical shifts, IR frequencies, or anything like that. You don't have to. So when you are solving problems, go take a look at the, you know, open up the page where they have the list of frequencies and solve the problem by looking at it. It's not cheating. It's just, you know, there's no reason to memorize that stuff. Okay, so we're still talking about physical properties, right? So that's when we talk about spectroscopy, we're talking about physical properties. So talking about physical properties now of carbonyl compounds and nitriles, we're going to talk about acidity and basicity. And so I've highlighted the non-bonding electron pairs of a carbonyl oxygen atom. And so you can imagine acid-base chemistry taking place. Acid plus base to give you conjugate acid. And this is a strong acid, -6. -6 means that this particular acid is about as strong as HCl. Okay? And so that tells you that this is not a very good base. Well, no, it's not. You know, it just isn't. So amides are much stronger. These are you know, 100,000 times stronger. And the reason is because the nitrogen, that one right there, is less electronegative than the oxygen right there. Okay, so the difference in electronegativity, remember electronegativity increases as you go from left to right, so CNO, N is before O, tells you that this is going to be lower in energy than that, placing a positive charge on a less electronegative atom. And so that's reflected in the pKa. Nitriles are really tough. I mean, this is a fantastically strong acid. So protonating a nitrile, getting the nitrile lone pair to react with a Lewis acid is just not very easy at all. So nitriles are really not particularly acidic. And actually, that plays out in the following way. The acetonitrile is a pretty good solvent for a lot of reactions. If it reacted readily with acids, or if it reacted readily with bases, it would be a lousy solvent for a lot of reactions. But in fact, it doesn't, and so it's fairly inert. Now, of course, that reflects itself in a reluctance of nitriles to undergo the kinds of reactions that we may want them to. Okay, so nitriles are reactive, but they're reactive only with really strong acids or really good aggressive nucleophiles, like alkylithiums. Okay, so all of this is a preamble to what? To what we're really interested in always. And what we're really interested in always are reactions. And what is related, we are always really interested in the mechanisms of those reactions, because without the mechanisms, we can't really understand fully what's going on. And so now let's get to the heart of it. So I just, what I talked about was the difference in electronegativity between carbon, nitrogen, carbon, oxygen. And so from back at the beginning of our discussion in 272, you know that when you have a polar bond between a less electronegative carbon and a more electronegative oxygen, less electronegative carbon, more electronegative nitrogen, that you always have this red dipole associated with that bond, with a positive end on carbon and a negative end on the heteroatom, the electronegative heteroatom, nitrogen or oxygen. And so what that tells you is that two things. First, what we saw, that the oxygen or the nitrogen with a partial negative charge is going to act like a base. Well, not a really good base here, but a reasonable, much stronger base there. What it also tells you is that this carbon atom and that one are going to react with nucleophiles. Okay, so nucleophilic addition is going to take place right there. Does that come as any surprise? I hope not, because that's exactly what we saw with ketones and aldehydes. And so now we just have another carbonyl. And so if this reacted in a completely different way, now that would be really surprising and puzzling. But the fact of the matter is, no, it reacts more or less the same way. So that's what you would expect. Okay, so let's talk about acid catalyzed hydrolysis of esters. Now this is an important reaction, and it is just the opposite, or the reverse, I should say, not opposite, the reverse of a Fischer esterification. When we talk about Fischer esterification, what kind of reaction was that? That was a reaction where we took the carboxylic acid, some excess of methanol or primary alcohol, catalytic acid, and then we used Le Chatelier's principle to push that equilibrium all the way to the ester. And so either we had to use big excesses of alcohol, or we had to remove water from the equilibrium, or very often we do both. And so, but we needed to use Le Chatelier's principle to push the equilibrium. Well, it's an equilibrium, then that means we can push the equilibrium the other way too. And so instead of removing water the way we did for the Fischer esterification, here we add water, lots of it. And so we, this is an acid catalyzed reaction. So the first step that takes place is activation of the carbonyl by protonation. Okay, this is the step that you needed to do for the first mechanism problem on the exam, right? You need to transfer a proton from the acid to, in that case, acetone, to activate the acetone towards nucleophilic attack by the phenol. Well, why is that? Well, you can say that, gee, why can't I do nucleophilic addition to that carbonyl? I mean, why do we need to activate it? And you're right, you should be able to do that, but here's the deal. You have acid, the protonated form is present, and the protonated form is going to be far, far more reactive than the unprotonated form. And so the mechanism needs to reflect that. And so, yes, nucleophilic addition here will take place, but nucleophilic addition here, we have a full positive charge, is going to be a lot faster. And so we show nucleophilic addition to the charged reactive form. So So this gives me from sp2 hybridized, as this electron pair starts to bond to that carbon atom, I get what? I get a rehybridization. So this carbon atom now goes from being planar to being tetrahedral. It goes from being sp2 to being sp3. This is exactly the way it always works. And so nothing I'm saying here is I hope, shocking. And so the first thing that happens is that we end up getting the tetrahedral intermediate. Now, the next thing is going to be proton transfers. And so what you're going to see is loss of a proton from here. The strongest base in acid is what? Is it hydroxide? Yeah, it's water. Don't make that mistake, okay? So when there's an acid catalyzed reaction, there's no hydroxide. When it's a hydroxide catalyzed reaction, there's no proton. So in a hydroxide, OH minus catalyzed reaction, what's the strongest acid? Water. So OH in water is going to be the strongest acid you're going to find in hydroxide. Why is that? Well, because if you had H plus, it would have reacted with hydroxide faster than anything. So it's gone, it's not there. So acid catalyzed reaction, strongest acid is going to be H3O plus. Talking about water now. Strongest base, water. Base catalyzed reaction, hydroxide and water. Base catalyzed reaction, strongest acid is going to be water, not H3O plus. Don't make that mistake, please. So, water is the strongest base you're going to find. That pulls off a proton. You protonate on the methoxy oxygen. You say, why did I protonate up here? Well, because it just gives you the same thing you started with, and that's what this equilibrium means, right? Or this equilibrium means. So the proton transfers take place reversibly. At some point, this one gets protonated. When it gets protonated, then I've converted OCH3 to CH3OH plus, and so now I have a really good leaving group there. And so that tetrahedral intermediate can collapse to give me the carboxylic acid, actually the conjugate acid of the carboxylic acid, and then proton transfer gives me carboxylic acid into my catalyst back again. And so acid here is used, I should say necessary, it's used to convert the methoxy into a much better leaving group. So instead of having a leaving group that's OCH3 minus in a poor leaving group, you have a much better leaving group, a neutral species. And so that's why it is this tetrahedral intermediate that collapses to acid and not this tetrahedral intermediate, because this would have involved generating OCH3 minus, something that is most unlikely in acid solution. Okay? So make sure that this mechanism makes sense to you. As I said, if I run the mechanism this way, it's the one you already saw. That's Fischer esterification. So you need to be able to do these, in both directions. Okay, so now we're going to talk about saponification. Saponification literally means formation of soap. And so this is the reaction that you use to make soap. Remember I said how you make soap? You take grease and you treat it with wood ash. And so you think, boy, that sounds like a pretty hairy thing to do. Why would anybody do that? Well, because grease is a series of glycerol esters. If I put hydroxy groups there, that's glycerol or glycerin. And so if I have esters like this, then this would be a triglyceride. So this is a triglyceride, so it's just an ester. It turns out these R groups are, if it's beef fat, this is a C17 piece, and if I hydrolyze that with wood ash, then I end up with 3 equivalents of potassium carboxylate. Okay, so that would be C17H, what is that, 34, 36. And so that would be my soap. And it's soap because why? Because I can form micelles with a polar head group and a lipophilic tail. And so that allows me to solubilize fat in water. Okay, so, but let's get back to the mechanism. So, We call this base catalyzed hydrolysis, but really it's not catalyzed because I have to use a full stoichiometric amount of base. So it should properly be called base-mediated reaction. I can't get away with just a little bit of base. You'll see why in a minute. So the mechanism is pretty much the same. I have a carbonyl compound, right? What do I know about that C double bond O? Whether it's an ester, a ketone, an aldehyde, whatever. I know that the bond is polarized with a positive end right there. I have a negatively charged hydroxide. What's going to happen? Positive, negative. Form the tetrahedral intermediate. Now there's no acid here. So here, methoxide has to act as the leaving group, no other choice. Now you say that, but it's a bad leaving group. Yes, it is. And so the equilibrium does favor this. But look what happens next. Now you have an irreversible step. This is a really strong base. This is a moderately strong acid. And so acid-base reaction takes place to give the carboxylate, and that's irreversible. And so even though the equilibrium favors this, you get a little bit of that forming, and then boy, it goes here. And Le Chatelier's principle, once again, make sure that it goes all the way to the carboxylate. Because once you get even a little bit of carboxylic acid in the presence of base, that thing is converted irreversibly to carboxylate. And so this reaction, that's why it requires a full equivalent of base, because all of this stuff is converted to this. So for every molecule of ester, you need one molecule of base. So you can't get away with catalyst here. Okay? Now, let me go through this again. Methoxide, OCH3 minus, lousy leaving group. How does this work? Well, I showed the arrows as being equivalent. They're not. Equilibrium favors this. But you get a little tiny bit of this happening. Once that happens, the next step's irreversible. It's gone. It goes off to the right. And so as long as the rate of the process is not too slow, reaction works. And so that's how you make soap. Okay? So, one other thing, yeah, because hydroxide is a really good nucleophile, much better than water, you don't have, no activation of carbonyls necessary. Okay, so when you have strong nucleophiles, then you don't need to activate the carbonyl. The reason you activate with acid is because you have, in that case, a not particularly reactive nucleophile, you have water. But if the nucleophile is hydroxide, or as we're going to see by and by, if the nucleophile is something like methyl lithium or butyl magnesium bromide or something, you don't need to do that. It's perfectly good aggressive nucleophile will attack the unactivated carbonyl too. So, to sum up, all of these reactions follow pretty much the same pattern. If you're an acid, you activate the carbonyl. If you're a base, you don't. You have a nucleophile forming a bond to the carbonyl carbon that gives you a tetrahedral intermediate. Then, depending on whether you're an acid or in base, proton transfers can take place, and you end up injecting a leaving group to regenerate a different carbonyl. And so they all work the same way, all of them. And so it's very important that you recognize that. Because what you don't want to do is you don't want to look at each addition to carbonyls, additions to the aldehydes, additions to ketones, esters, we're going to see amides, and look at them as a different reaction. Yes, they're different reactions, but they do share a lot of common features, and those common features that you want to make sure that you understand and recognize. And so that's, again, why we talked about mechanisms. So they all work this way. You have some kind of X group, nucleophile, gives you a tetrahedral intermediate, collapses with loss of X minus to give you a product. They all work that way. You say, yeah, but the ketone ones don't work that way. Well, take a look again and see that actually they look an awful lot like that. They're not, maybe not exactly the same, but very, very similar. And so in all cases, what you're doing is you have a positively charged carbonyl carbon reacting with an electron pair from something. Okay, they all share that common feature. Okay, so now let's take a look at lactones. Lactones are, well, what's a lactone? lactone's a cyclic ester. So we just looked at esters, now we're going to look at lactones. What's the difference? Essentially none. Okay, not much difference at all. Lactones are esters. You know, if esters react one way, lactones will react pretty much the same way. So, if I do a base-mediated hydrolysis of the lactone, I'm going to get the carboxylate. Well, you're going to say, yes, but you have the hydroxy group here. True. That I will end up protonating the alcohol, but the mechanism is the same. So one thing to remember is that the mechanism for this reaction is not, although sometimes this will happen, this is not what happens, okay? It's not doing that. That is not the way it works. It works the same way we saw before. The hydroxide, it gets started with the hydroxide attacking the carbonyl and forming a tetrahedral intermediate. So what happens is that you end up getting the and this is reversible, of course, and then it does the same kind of chemistry you saw before. Okay, and so please, remember that just because it's cyclic doesn't really mean anything. It's just the same thing. So if I just ignore that chain being there, then the mechanism is identical. Now, one difference: if I take the hydroxy acid, okay, and I treat it with acid, then in the case of the 5-membered ring, the lactone is formed spontaneously. So the hydroxy acid, if it's going to form a 5-membered ring lactone, the 5-membered ring lactone is favored at equilibrium. So very easy to form. Okay, equilibrium pretty big. In other words, 160 means, if there's one of these, there's 160 of those. So that's, that means what? About 0.5% of that. So that's a complete reaction by anybody's reasonable definition. 6-membered ring, not really, 3.3. So, say a 1 to 4, 1 to 3, 1 to 4 ratio. And of course, if I go to a 4-membered ring, there's what? There's strain. And so here, the open chain form is going to be favored. So none of this stuff should surprise you, right? Because the 5-membered ring places the hydroxy group and the carboxylic acid just a little bit closer than the 6. And that statistically means that the closure of the lactone should be easier to form the 5-membered ring lactone, not nearly so easy to form the 6. For the 4-membered ring, 3-membered rings, 4-membered rings, a lot of strain. So this is a compressed spring, and it pops open, okay? So think of strain as being like a compressed spring. You give it something, and spring, it opens up, and there it is. So this process is driven all the way to the right by relief of strain. This process is driven to the right by just a statistical effect. In other words, this hydroxy group is on average pretty close to that carbonyl. And here, this hydroxy group is not as close to that carbonyl because you have an extra CH2 group. Okay? So all that kind of makes sense. The one new point here is that this closure is really easy and pretty much spontaneous in the presence of acid. Okay, so now we're going to talk about amide hydrolysis, and amides can be hydrolyzed under, just like esters. Amides can be hydrolyzed under either basic or acidic conditions, but because amides are more stable than esters, you're going to need to use forcing conditions to hydrolyze them. And so let's take a look here, and then I want to kind of make you think about something. Okay, so let's take a look at the mechanism. Now, this mechanism by now, I hope, looks just like the last one. Okay, so it doesn't look any different. The only difference here is I've got nitrogen instead of an oxygen, so nothing changed. I activated the carbonyl, nucleophilic addition, gives me a tetrahedral intermediate, proton transfer, strongest This is acid catalyzed. The strongest base is water. No hydroxide in acid. Water is the strongest base. Get proton transfer. Reversibly, at some point, the nitrogen gets protonated. Collapse of the tetrahedral intermediate with generation of ammonia. Conjugate acid. The acid, this is a base, that's an acid. You end up getting the ammonium salt and the carboxylic acid. Okay, so this looks just like the reverse of the Fischer esterification. It looks just like the acid-catalyzed hydrolysis of an ester. Nothing different, essentially nothing different. Okay, so work through one of these, work through two, however many, but at some point this has to become second nature. Now, this is a reaction that again needs to use not catalytic, but stoichiometric acid. And the reason is because this you're forming a fairly strong base, and so this has to be protonated completely. So you're not going to use 10 mole percent acid, you're going to use over 100 mole percent. Now, when you go to the base catalyzed hydrolysis of amides, there's a problem. Reaction works. So the problem is with the way we show it and the way we understand it. So with base, there's no need for, first of all, there's no acid present. If it's aqueous hydroxide, I don't have any protons around. So I can't activate that amide oxygen atom. Yes, the amide oxygen atom does have a delta minus there, but no, there is no chance to find a proton in hydroxide. And so hydroxide, which is an aggressive nucleophile, attacks the carbonyl without activation. It forms a tetrahedral intermediate, which is charged. No proton transfer is necessary. And then tetrahedral intermediate, just as we've always seen, collapses to give the acid the formation of NH2 minus. Oops, what's wrong with NH2 minus? Well, it's the conjugate base of a very weak acid. How weak is ammonia? pKa 35. Oops. So does that look like a leaving group to you? I hope not. That looks like the world's worst leaving group, but the reaction works. So what's going on? Well, you can say that, well, it's going on because, the equilibrium is tiny and whatnot. Yeah, that's true, but there's another reason probably. And the book doesn't go through this, but here's the way to think about this. You actually don't. Okay, so we can show it this way, and we haven't violated any rules or anything, but it doesn't have to proceed exactly that way. There's another way it can proceed that gets you away from this awful problem of generating directly NH2 minus. Okay, so here's how you think about it. Look. This reaction is run in what solvent? Tell me again. Yeah, water. Yeah, okay. It has hydroxide, correct, but the solvent is water, correct. Okay, so let's redraw this thing here. Okay. This is in water, isn't it? What do you think that lone pair can do in water? It can hydrogen bond, can't it? If it's hydrogen bonded, then as you collapse this intermediate, you don't ever have to form a free NH2 minus. You form a nitrogen atom that's got a partial negative charge, but as you're breaking this bond, you're also forming that one and breaking that one. And so, yes, in the transition state, this will have a partial negative charge, but you never have to generate NH2 minus. Never. All you have to do is form a bond from the nitrogen to that proton, to that hydrogen atom, and at the same time that you're forming that one, break that one. And that gets you away from trying to explain away why NH2 minus can act as a leaving group, which probably it cannot. And so, so that's how this can be. So this process takes place pretty much as shown. All I've done actually is I've shown, instead of showing 2 steps, I've shown essentially one step. So this is a common way that organic reactions that look as if they can't work can work. Well, let me just take a little detour here so you can understand what that means. In your book, you've seen it mentioned a few times that concerted reactions, those are reactions that take place, everything happens in one step, very often have lower activation barriers than the equivalent process that would be stepwise. So if there are two pathways for things to react, one is stepwise, one is all in one step. Almost always, the one in one step is the one that's easiest, has the lowest activation barrier. Why? Well, because in that single step, you're doing a couple of things. You're breaking bonds, that costs you energy, but you're also forming bonds, that lowers the energy. So overall, you don't have to go up as high an activation barrier. Why? Because I'm not just breaking bonds, that cost me energy, I'm also making bonds. And so it's the same thing here. Instead of busting the bond from carbon to nitrogen, generating NH2 minus, I can be breaking that bond and forming the NH bond, and that lowers the activation energy for this kind of a process. So the mechanism I showed you was kind of, it combined two steps, and that's why it would be lower in energy. Okay, so base catalyzed hydrolysis of nitriles, acid catalyzed hydrolysis. These reactions work, but they require forcing conditions. Acid catalyzed hydrolysis, I said amids, I meant amids. Acid for nitriles, even worse. Okay, so nitriles are really tough nut to crack. And so, but the mechanism is almost the same. Not exactly the same, but almost. So here's what happens. First step, acid catalyst, obviously. First step, proton transfer. Now, you already know that the equilibrium is going to be far, far, far to the left here. Why? Well, because the pK of this thing was what did we say? It was minus 10 or something. And so, and the pK of hydroniumine is a long ways away from that. And so, you have just a little bit of this protonated form. And then the strongest nucleophile in acid is going to be water, hydroxide. It adds to, well, where does it add? Can it add to nitrogen? Well, let me ask you a question. Nitrogen is positively charged. Gee, how come the water doesn't add to nitrogen? It's a trick question. Yeah, because of octet wall. There's no way it can. And so this nitrogen atom is a complete octet. No way can you violate that. So the water, the electron pair adds here. Push arrows, I end up with this. And I can lose a proton. So it looks pretty much the same. Activate the carbonyl, activate the nitrile, nucleophilic addition, proton transfer again, and now you end up with something we haven't quite seen before. This is by the way called an imidic acid. Don't worry about that. Just think of it this way. Look, if I had an oxygen atom here, that would be an acid, wouldn't it? And if I had an R group here, that would be an imide. And so that's why it's an imidic acid. But it looks pretty much like carboxylic acid. I have an OH, double bond, nitrogen, one pair, electron transfer, and so on. And so it follows pretty much exactly the same paradigm that we've seen again and again and again. Take a look at this at your leisure. It's in the book. Make sure that you can reproduce each and every one of these mechanisms. I mean that. Take a blank piece of paper. Make sure that you go from start to finish without screwing up. Without having a hydroxy group coming out of nowhere, charges appearing where they shouldn't be, or any of those other things I've seen on some exams. And one other thing, I didn't give you hell about a couple of things. I had it on my. Okay, so first of all, yeah, the last question on this exam, I changed something just a little bit. Wasn't that mean? Because I knew that a lot of you were going to memorize the answers from the last one, just spit it back at me. And sure enough, a whole bunch of you did exactly that. Don't memorize, okay? Try to understand that. It's not that hard. So don't memorize. It's not going to help you. Next time I'm going to do it again, maybe. And yeah, I'm going to keep you guys guessing. Now, that was one thing I wanted to tell about. The other one is this. Quite a lot of you did much better on this exam. That's great. Now, make sure that those of you who did much better on this exam don't backslide and screw up the third one. Why don't you want to do that? Because if you do that, I promise you, there'll be endless grief for you. Even just endless grief if you do that. So don't. You did well on this one. What that means is that you're studying right, you're doing all the work. Don't now get lazy and say, oh, I can pass the class, I don't need to do well in the next one. Don't do that. Because I've been very upset if I see that, so don't, please. Okay, end of sermon. So protonation, nucleophilic addition, proton transfers, all the same. Make sure you can do that, okay? It's not that hard. Emitic acids, I said, this is the only thing that's new. An emitic acid, it looks pretty much like something we've seen before, doesn't it? It looks like an enol. Looks just like an enol, doesn't it? I mean, if I had carbon there, it would be an enol. And so the conversion of the emitic acid to the amide is also very similar to another reaction that you've seen. It looks very much like an enol to ketone polymerism. In fact, it is. And I mention that because you need to make these connections, okay? So if you think of the enol ketone being one reaction, if you look at this one, say it's a different one, then you're missing the connection, and it's harder to keep this all straight. But the other point, this is serious, is it's all acid-base chemistry. Remember how much time we spent with acid-base chemistry in 272? It's kind of boring too. Well, you know what? It's important. And it just keeps coming back again and again and again. And so if you don't understand acid-base chemistry, this stuff it's not gonna gel. So, yeah. Okay, so we saw acid-catalyzed hydrolysis of esters and amides. We saw base-mediated hydrolysis of esters and amides or whatever. Same thing with nitriles. And once again, the nitrile is much less reactive than an ester or an amide, so this requires heat and time. Hydroxide, so no proton and base, so no activation. Hydroxide adds, this is the conjugate base of the amidic acid. This is a strong base. It's protonated by the strongest acid in aqueous phase, which is water, not H3O+. The amidic acid loses a proton and gives you so I add a proton and then I lose that one, and then I add one again, and I end up with the amide. So it follows pretty much the same logic that we've seen, not much different. Nucleophilic addition to the positively charged, in this case nitrile carbon atom, proton transfer, and so on. And eventually end up with the amide and the hydroxide back. Now, acid chlorides and anhydrides, these undergo very rapid hydrolysis. In fact, you don't need any kind of catalyst, you don't need nothing. All you need is moisture in the air, and they react, which is usually what you don't want. So why is that? Why is it that if I have an amide, I've got to really, boil the heck out of it with base or acid, whereas if I have an acid chloride, that I don't really need any activation. Water will add to that very fast, no activation, no nothing. Well, it's because that chlorine is pulling electron density out of the carbonyl. And so this carbonyl is much more reactive. Now, there's another reason too, and we're going to go through that in a minute. So it turns out that when you have a group that is either a chloride or an acetate or any kind of electron withdrawing group, any kind at all, attached to the carbonyl, and nucleophilic addition to that kind of carbonyl takes place with a very low activation barrier. And that's for two reasons. Okay, so before we talk about the reasons, let's just go through the series here. And this is something you do need to know. So acid chlorides and hydrides, that's at the high end of the reactivity scale. Nitriles at the low end. And so esters probably a little more reactive than acids, much more reactive than amides. I haven't included ketones and aldehydes here because that's a little bit like apples and oranges. But ketones and aldehydes are here, okay? So aldehydes first, then ketones, then esters and whatnot. But these are very, very reactive, not reactive. Now, why is this? I already said one, I gave you one factor. When you have an electron withdrawing group attached to the carbonyl, like the way you do with the acid chloride or the anhydride, then you're activating that carbonyl, and you have a good leaving group, but also you're diminishing the stability of the starting compound. Now, why is that? Well, because remember the IR stretching frequency for an acid chloride. That's a very stiff bond, and the reason is because the acid chloride is not resonance stabilized. It's not resonance stabilized because of the electron withdrawing effect. So when you have an acid chloride or when you have an anhydride, the starting ketone, or the starting carbonyl, pardon me, is higher in energy than it otherwise would be. And then the leaving group, chloride acetate, is much, much better than amide. And so those two factors contribute to making the acid chlorides reactive. Now, one way to do this is in terms of an energy diagram. And so when we talk about energies, or something being higher or lower in energy, remember I told you that the question you always want to ask is compared to what? Okay? And so if we're going to talk about this as being a, so we're talking about this reaction. We're talking about hydrolysis of an amide, then compared to an ester. Okay, so we'll take the ester as being kind of the average, if you will, the point of comparison. And if an ester had a delta G naught here, then the amide is lower. Why is the amide lower? Well, because the nitrogen is less electron withdrawing than the oxygen. And so I've lowered the energy of the starting material, and then the first transition state is to get the tetrahedral intermediate. The second transition state is to spit out NH2 minus as a leaving group. Well, it doesn't have to be NH2 minus, I already explained that, but you know what I'm saying. So it's splitting out the leaving group. Now, this is, the energy for that is raised relative to an ester because this is a poor leaving group compared to OR minus. And so you're lowering the energy of the starting material and raising the energy of the transition state. And that's why nucleophilic additions of amides are going to be much slower than nucleophilic additions to esters. And you can make the same argument for acid chlorides or anhydrides, except there, instead of going down, you're going to go up and down. So, to recap here, when we say energy lowered or energy raised, compared to what? And so for here, the point of comparison makes sense, ester hydrolysis. Okay, let's quit here. I have your exams. Because there's another class coming in, why don't you go outside and I can distribute what's left.